Jai Hind, welcome to class of Analog and Digital Communication. So, we'll start with amplitude modulation today. Before that, we really need to understand what modulation is. Whenever we communicate, that is, the exchange of information between a transmitter and receiver takes place. That is done for a need. An information has to be transmitted to a particular place, that has to be interpreted, that has to be received properly, that has to be interpreted, right? So if we are talking if we talk about the information which is audio signal, which ranges from 20 to 20 kilohertz, and we are talking in person, that kind of communication is feasible. But let's suppose the receiver is at a far distance from the transmitter, then the voice communication, the audio communication physically won't be feasible, because there is a long distance that has to be covered. So in that case, we have to implement some things on the information signal. Like if a person is sitting 500 meter beyond or 200 meter beyond, maybe we can use a loudspeaker, right? But if a person is in another city or in another country, then using even a loudspeaker won't help. We have to think of some permanent solution that will serve us, right? So modulation is a process of transmitting my low frequency baseband signal in such a way so that it reaches far distance, right? So it is shift of the range of frequency in a signal which is accomplished using this technique, which is called modulation. So it can be technically defined as the process of varying the characteristic of a high frequency carrier wave with respect to the instantaneous value of the message signal or the modulating signal or the information signal, right, which is usually a low frequency or baseband signal. The baseband signal is referred to as modulating wave, and the result of the modulation process is referred to as modulated wave. Modulation is performed at transmitting end, and modulating signal is considered as the voltage signal. So, what is basically modulation? In modulation, let us consider it is a black box, and we give two kinds of input to it, the message signal and the carrier signal, and what we get as a result is my modulated signal. So what happens basically? We need to understand the process of modulation. We need to understand first of all what is the need of it. So if I talk about the need of modulation, the first need is to reduce the antenna height. And how do we reduce antenna height? With the help of modulation. It can be explained with the help of a frequency. Let's suppose we consider a frequency which is 10 kilohertz that has to be transmitted. We know that from Einstein equation, C equals to E equals to mc square, or we can relate the velocity of light equals to velocity of light can be related to the frequency and wavelength in such a way, right? And we know that height of antenna is proportional to the wavelength. In what way? 1/4 of it. So we can see from here, if my frequency is low, then lambda would be too high, right? Because the multiplication is a constant, right? If this is low, this has to be high. When this is high, the height of antenna will also be high. So let's take example of 10 kilohertz frequency. In such a case, the antenna height for 10 kilohertz wave, my antenna height would be impractical. But if instead of 10 kilohertz I take 10 megahertz, then I will get a value of antenna height which is practical, right? So the major reason why we need modulation is to reduce antenna height, because we cannot really install antennas which are 1 kilometer or 1.5 kilometers tall, right? We can there is a practicality to antenna height. We can install antennas which are few meters tall, right? So if we want to do long distance communication, we can install tall towers, but installing tall towers has also got a limitation that the height has to be practical. So one of the major reasons for using modulation is reducing antenna height. If we talk about the another reason, then reducing the interference. If all the audio signals are transmitted as it is, we know that audio frequency ranges from 20 hertz to 20 kilohertz, right? So there would be interference at the receiver. But if we do frequency shifting, one of the audio frequency shifted to some other frequency, another message signal, or the audio frequency shifted to some another frequency, and then it is passed using the same medium, then for at the time of reception of it, the receiving and interpreting and segregating the signals will be quite easier, right? Another reason why do we use modulation is better use of multiplexing, right? So there are several reasons why we need modulation. So after that, if we need to understand what is modulation, how does it happen? So modulation will be a black box to which one of the input is my baseband signal, another input will be my high frequency carrier wave. So one thing we got to know from here, I want to transmit my low frequency signal. I cannot use a very low frequency signal. I can transmit a high frequency signal, but I cannot explicitly vary the frequency of my message signal like that, right? If I vary the frequency of my message signal, I will lose the essence of my message, because what is an analog wave, right? Xt would be if it is a sine wave. My signal does have amplitude and angle, these two characteristics. What if I change the frequency? If I change the frequency, my message will be altered. That is, I will lose my information. I'll lose the essence of my signal, which is not at all preferred. So I cannot directly play with the frequency of my message signal. However, what I can do is, like, you need to go to a place which is 10 meters beyond you. You can walk 100 meters, 200 meters, 1000 meters. Okay, you can walk, but you need to walk to some other city. Will you prefer to walk? No. You will preferably take a bus, car or train, any mode of transportation, because that is faster. So in similar way, modulation could be explained that if I need to transmit my signal to longer distance, then I will not send my signal as it is. I will make it board some high frequency signal. So that high frequency signal will carry my message signal to long distance, right? So that is what I do. I do not change the frequency directly, because in that way I'll lose my message. My message will be altered. However, I can use a high frequency signal. If this is my message, such frequency appears to be high frequency compared to that. So I will make my signal board this signal. So in some books or somewhere you may find the definition that superimposing the signal on it, but I will not preferably use that term. It is not superimposition. It is actually altering the characteristic of this high frequency carrier wave with respect to this, so that this carrier somehow takes the identity of this message, but its frequency remains the high frequency, and this high frequency wave is capable of traveling longer distance. So this high frequency wave will act as a carrier for my message signal, and that process is called modulation, right? I hope it makes a little sense. So baseband signal or the information signal or the message signal is my low frequency signal, actual information signal, and my carrier is a high frequency signal which will act as a carrier for this message. And when I pass these two through this box, what I will get will be the resultant wave. Now, if I want to classify what kind of modulation I am using, that will depend on which characteristic of my carrier wave is altered with respect to the baseband signal. Like, what all characteristics a simple sine wave has? It has amplitude and it has angle. If the amplitude of my carrier wave is altered with respect to the instantaneous value of my message signal in such case, suppose I represent my message signal with xt, or I might represent it with mt, and I'll represent my carrier wave with the representation ct. Ct equals to a1 sine omega 1t. I am trying to make this look different from the message amplitude, make this angle different from the message angle. So I have to consider my message signal always as a voltage signal, right? So according to the voltage of my message signal, if I vary the voltage or amplitude of my carrier wave, that kind of modulation will be called as amplitude modulation. And if according to the voltage or amplitude of my message signal, I vary the angle, that is phase or frequency of my carrier wave, phase or frequency of my carrier wave, then that kind of modulation will be angle modulation. Within angle modulation, I may call it as frequency and phase modulation, right? So these are the types of modulation that we'll be discussing. So like the need I have explained earlier. So if I talk about a voice signal that frequency is up to 3 kilohertz, if I talk about, right, if I use a microphone and transmit it, I know the audio frequency ranges from 20 hertz to 20 kilohertz. Let us consider the frequency that I consider is 3 kilohertz. For 3 kilohertz wave, I know C equals to, so my lambda will be C by F, this is F, right? So at 3 kilohertz, my lambda comes out to be 100 kilometers, right? So here we can see, if even if the size of antenna required is 1/10 of the wavelength, then also the antenna will be too large to install, which is the impractical height, right? So need of modulation is explained here: reduction in the antenna height, increasing the range of communication, right? We can do it for long distance. Frequency assignment, we shift our frequency to some other level, so we assign it a new level. Reduction of noise or interference, true. Multiplexing becomes easier, bandwidth limitations of equipments is resolved, and frequency characteristics of antenna in a better way, right? So these are the need of modulation that I have already explained. Then when we vary the characteristic of my carrier wave with respect to my message signal, which characteristic I vary, that will decide which kind of modulation I am talking about. If I am classifying my modulation on the basis of my input message signal, so I'll simply take, if my input message signal is analog wave, I'll call it analog modulation. If my input message signal is digital, right, with fixed values of message signal like 1 and 2, 1 0 bits, right, then that kind of modulation will be my digital modulation. In analog modulation, a higher frequency signal is generated by varying some characteristic of a high frequency signal on continuous basis, and if I further classify it, I have amplitude modulation, frequency modulation and phase modulation, abbreviated as AM, FM and PM. Here we have infinite number of baseband signals, true, because such kind of wave I can have infinite numbers, right. In digital modulation, signals are converted into binary data, that is, we know that all the naturally available signals are analog in nature. So if I am trying to perform digital modulation, then first my signal has to be converted into digital form. So about the conversion of a signal from analog to digital form, we'll be talking, right. So when we discuss actually digital modulation after analog modulation, right, signals are converted into binary form, encoded, then transmitted. Such kind of modulation can be amplitude shift keying, frequency shift keying, phase shift keying, quaternary, then these are variants of PSK, and this is a quadrature of AM. More complex, but it reduces the effect of noise. We know the advantages of digital communication over analog communication. One of the prime advantages is reduction in noise, right? Because a noise will affect such kind of signal more, whereas to actually cause an error, the level has to go from 1 to 0 or 0 to 1. So, which is little difficult than this case. We have finite number of baseband signals here. If I talk about performance of a radio link, to determine how well a link perform, we need to know signal to noise ratio and modulation scheme. So actually, being communication engineer, we really need to understand what kind of communication system we are talking about. And when we study communication, noise is an integral part of it. So noise is separately studied. So SNR is an important factor, signal to noise ratio, that is average power of signal divided by average power of noise. It is always calculated at receiver, and we see if the tolerance is good and the SNR value is high, that kind of communication system is preferred. Another, what kind of modulation scheme I am using, whether I am using analog communication or modulation or digital modulation, and within that what kind of actually scheme I am using, like AM, FM, PM or ASK, FSK, PSK. So these two are the prime factors that will decide the performance of my radio link. So in whole and whole, when we study about communication system, we need to understand this. What is continuous wave modulation or analog modulation? Sine wave carrier is described by 3 parameters: amplitude, frequency and phase. Frequency and phase modulations are combiningly known as angle modulation, as discussed before. Now let's start with amplitude modulation. What is amplitude modulation? Here the amplitude of my carrier wave is altered in accordance with the instantaneous value of my modulating signal or message signal or the information signal, right? A carrier is represented, a carrier may be CT, represented by amplitude Vc, and if it is a cos wave, omega is represented at 2 pi f. F subscript c represents the carrier frequency here, T, and this represents the phase difference here. Let's see what does my modulating signal can be, how I can represent my modulating wave or the message signal. That can be represented with Vt, Xt or Mt. Vm represents voltage or amplitude of my message signal. This is a cos wave, 2 pi fmt. Doing cos relations will be, cos trigonometric relations will be easier to understand. So we are considering cos wave here. Even carrier and message both, see, we can consider both as sine wave, one as cos, another as sine. Considering both cos, the trigonometric relations are quite understandable, right? So, and easier to memorize. So, we consider both the signals as cos wave. Information is contained in the envelope. Let's see how does carrier wave, modulated wave looks like. If this is my message signal and suppose this was my carrier wave, a high frequency, constant amplitude, what has happened here? I have tried to change the amplitude of this carrier wave with respect to the amplitude of my message signal. Then what is observed? See, with increasing amplitude of my message signal, the amplitude of carrier wave is increased, whereas phase and frequency remains intact, the same. So here I can see gradually the amplitude increases as it is rising and it decreases at the falling edge of it. Right? Here it's the minimum, right? If I draw a reference 0 as well, see, this is the minimum height it attains, this is the maximum height it attains, this is corresponding to this minimum, this is minimum, this is maximum, right? So when I alter the amplitude of my carrier wave, keeping its phase and frequency intact or constant, that kind of modulation is called as amplitude modulation. This is my modulating signal, message signal or the information signal. This is my carrier wave and this is the resultant or the amplitude modulated wave. This is the time axis. I hope this is clear. So this is the resultant wave, which will be the outcome of my modulating modulating box, right? So here the modulated signal can be represented as Vt equals to Vc cos, because carrier amplitude will be varied and somehow the phase and frequency remains constant. So when I add both the signals, like one over another, the amplitude, this is the final expression that I get, Vc cos 2 pi f ct 1 plus m cos 2 pi fmt. This is something that we need to understand. That is the modulation index, which we'll understand, I'll explain in the next lecture maybe. So Vc is my unmodulated peak carrier amplitude, Fc is my carrier frequency, Fm is my modulation frequency and m is my modulation index, right? About modulation index we will talk in the next class. We will talk about all of this. These are the references which I have used. Thank you.